A compliance request comes in. Delete one customer's rows from the swipes table. A few dozen rows out of 2 billion. Somebody runs the delete. It works. And it rewrites 400 files to do it. At roughly 128 megabytes a file, that's about 50 gigabytes of data rewritten to remove a few kilobytes of rows. 20 minutes of compute for a change that should have taken a second. A single row highlighted red inside a folder packed with file icons. Arrows show 400 files being rewritten with a caption, minus 50 gigabytes rewritten to delete a few kilobytes. That's annoying, but it's the mild version of a problem that got serious enough at a big enough company that they built a new kind of table to escape it. Start there because the origin story explains the design better than the design explains itself. Netflix moved its data platform onto Cloud Object Storage, S3. The tables were Hive tables, which at the time was simply how this was done, and Hive's model of a table is exactly the assumption we're about to kill. A table is a directory, and its contents are whatever files happen to be in it. There's no list of what belongs. There's a folder, and you look inside. A folder labeled Table, filled with file icons, a magnifying glass over it captioned, "What's in the table? Look and see." At small scale, that's fine. Take our swipes table instead. 400 gigabytes arriving daily, 2 years retained. That's roughly 300 terabytes, partitioned by day into 730 folders, holding somewhere north of 2 million files. Now the 4 problems, and they get worse as you go. The first is speed. To plan a query, the engine must discover which files exist, which means listing directories. On a local file system, that's fast. On object storage, each listing is a network round trip, and against 2 million files, planning can take longer than the query. The engine spends its time asking what's here before it can start reading. The second is atomicity. A job writing to a Hive table drops files into the directory as it goes. If it fails halfway, those partial files are already there, and since the table is defined as whatever's in the directory, the table is that broken intermediate state. Worse, a reader running at that moment sees it. There's no instant where the change flips from not done to done. It dribbles in. The third actually frightened people because it doesn't announce itself. Object storage at the time was eventually consistent. You could write a file, immediately list the directory, and the list might not include it yet. When a table is defined as whatever the listing returns, a stale listing means an incomplete table. The query doesn't error or warn. It returns a number that's quietly, invisibly wrong, and every dashboard and model downstream consumes it as correct. The fourth is schema. Hive tracked columns largely by name and position, so renaming, reordering, or dropping one could cause old files to be read under the wrong assumptions, data lining up against the wrong column, again with no error. Changing a table's shape became something people avoided rather than something they did. Look at those 4 together and notice the single root cause. Every one exists because the table has no explicit definition of itself. It's inferred from the folder every single time somebody asks. The obvious question is why not put it in a real database and be done? Because of what you'd give up. 300 terabytes on object storage is cheap, precisely because that storage is dumb. It holds objects and nothing else. And it's in open formats many engines read directly, so no vendor owns access to it. Loading that into a warehouse means paying far more to store it and handing one system control of it. The goal was never to move the data. It was to leave the files where they are and put a real table on top. So Ryan Blue and Dan Weeks, working at Netflix, built something on a different premise and open-sourced it in 2018. It became an Apache top-level project in 2020. The premise? A table is not a folder. It's a tree of metadata pointing at data files, and that tree is the table. Build it bottom up. At the bottom, ordinary Parquet data files, unchanged. Above them, manifest files, each holding an explicit list of data files plus statistics on each, row count, and the minimum and maximum value of every column inside it. Above those, a manifest list, naming every manifest in this version of the table, and at the top, one small metadata file describing the table's current state, schema, partitioning, and which manifest list is current. Now watch a query. It reads the metadata file, which points at one manifest list, which names the manifests, which name the data files. At no point does the engine list a directory. It follows an explicit chain from one small file to an exact set of data files. And because manifests carry statistics, most data files get eliminated before anything opens them. Query one day out of 730, and the other 729 partitions are ruled out from metadata alone, no bytes read. Within the surviving partition, a file whose amount column tops out at 50 pounds can't contain a 200-pound transaction, so it's skipped too. Here's the number that makes the whole design click. 300 terabytes of data, 2 million files, described by a metadata tree measured in megabytes. Planning a query stops being an interrogation of storage and becomes reading a few small files. That's problems 1 and 3 gone at once. Planning walks a tree instead of listing a folder, and correctness no longer depends on a listing being fresh, because nothing is inferred. Every file that belongs is named explicitly. Then there's writing, and this is what makes the next 2 videos possible. Iceberg never edits a file in place and never drops files into a folder hoping someone notices. A write produces new data files, a new manifest describing them, a new manifest list, and a new metadata file. The old metadata file still exists, complete, still pointing at the old manifests and data files, all of which still exist too. Each of those complete trees is a snapshot, a full, consistent picture of the entire table at one moment. Writing doesn't modify a table, it adds a snapshot alongside every previous one. And snapshots share data files. One day swipes landing means about 3,000 new files. The new snapshots manifests point at those, plus the 2 million that were already there, untouched. A new version of a 300 terabyte table costs a few megabytes of new metadata, not a new copy of anything. So a table isn't a folder you inspect, it's an explicit tree, and every write produces a new version of it while leaving the old ones alone. Which leaves one question. If every write creates a new snapshot and all of them exist at once, something has to decide which one is the current table. Where does that live? And what happens when 2 jobs try to change it at the same moment?